Great. Okay, so our recording's in progress. And yeah, so I've been working on this segmentation code with some people in Andrew's group, including Mina, for a while now. And so I'm just gonna take you through the workflow. Sorry, I'm just, I should share my screen so you can see what I'm doing. Okay, so yeah, I'm gonna just take you through kind of how the code works. So basically, we're doing all of this in Google Colab. You don't have to do it in Google Colab. You can, with some minor adaptation, run the code on a HPC, like a high performance computing node, or run it locally if your video card is good enough. So I'm using Google Colab because it's easy to share code on. The code will run when you do share it. And I pay for like a more expensive version of Google Colab. It's about $50 a month, but it gives me access to an A100 video card, which is probably one of the best video cards in the world. It's $11,000 on its own. So, you know, $50 a month is pretty cheap. Anyway, so with that, I'm just gonna kind of take you through this. So to get started, I'm gonna just take you through kind of like everything you need to do to kind of run this on your own in the future if you wanted to make a new notebook. So we're gonna populate a couple folders into this folder. So we're gonna put a best models folder in here. And I know this may seem a little out of sync right now, but it'll make sense in a second. And then we're going to put in a train folder, and then we're going to put in a test folder. So the idea here is that we are going to train models off of images and annotations, and we are going to save those models in this best models folder. And then after we've done all the training, we can independently verify how good our model is by testing on images that are in our test folder. And so I'm just going to upload some images here now. I got these ready kind of ahead of time. So this is the train. So we'll just put these here. And then we'll do test as well. And so anyway, those are uploading right now. So these are just your classic like annotated leaves that I'm sure you've all seen. So we can just take a look, right? So we have CT scans of individual leaves like this. So this is Juglins from Mina. And so that's the CT scan. Oh, and here's the corresponding mask, right? So Mina was kind enough to go through and annotate these, and yeah, so she has put in annotated the background, the epidermis, the mesophyll in black, air spaces in white, veins in this light gray, and then in this middle gray are the bundle sheath extensions. And so once you've like populated these different folders, everything's pretty easy to use. So you can open up your Colab notebook at that point. And so there's this, let me see if I can move this out of the way. There's this table of contents over here. And with this, you can kind of move around the code to different areas. And it may look pretty intimidating, but I can hide a lot of the code. And then it will look less intimidating. And you don't actually have to change that much. So the idea is the first thing you have to do is you're going to connect to your Google Drive. We're already connected to Google Drive, so there's not much that we have to do. But what you would have to do is like enter your Google password to be able to connect to your drive. And this links the Colab notebook to your drive, so it can read and write from your drive. And then I have this step here just so you can see what video card that you have. It's nice to know the video card you have. You're not always allocated the same video cards. And so I'm on a A100, right, with 40 gigabytes of VRAM. It's a lot of VRAM. If you go with the unpaid version, you'll probably be on a K80, which has less VRAM. It may have 11 gigabytes of VRAM. You also might get allocated a P100 or a V100, which have 16 gigabytes of VRAM. It's nice to have the 16 gigabytes of VRAM. So there's a $9.99 a month version of Colab that will definitely get you the 16 gigabytes. And that's because, so here I was working on kind of training a model before this meeting. And you can see here that I'm using 12,000 megabytes. So 12 gigabytes of VRAM on the video card. And so if you're on an 11 gigabyte video card, you won't be able to train the model necessarily. We have ways around that, but just as a heads up. And I can just get rid of this. We don't need that. So then the next code block is this materials code block. And I'm going to change this in real time. So we have this FCN workflow for Craig. So this is just where you would enter like whatever folders that your images and masks are in, you would enter them right here. You also can, I guess I should show this first as well. You should show, or you should put in your materials. That's what we're calling it. So these are like the tissues in your leaves. This code also works. I mean, it works for anything. So you can run with some modifications, you can do RGB images if you have leaves on like a board that you want to segment, or I don't know, we've done like wheat stems or cranberries. So it's worked for those. But basically, here you put in the materials that you want to identify. And for the masks that you make, you input the grayscale values. These are in triplicate because the code is designed to run with RGB images, red, green, blue, not just grayscale. And so you basically put your grayscale value 0 to 255 3 times into the code. So this is the grayscale value 85, but it's 85, 85, 85, because the code's actually looking at all 3 layers. It's looking for 3 layers in an image. So then we can just change some of the file names here.
Devin, real quick,
Yes.
what were the other parameters following the pixel values?
Oh yeah, good call. So these are output values right here, the 30, 150, 255. So this is just what the grayscale value is gonna output to. It works-ish. So one of the problems is it works really well with like binary. Like say you're trying to do binary classification, it works great. But the way we stack the materials ends up that this will add up to some number that's greater than 255. And so we end up like having fractional values. Anyway, the output's still fine. It just won't necessarily be exactly like this grayscale that you want. So you'll have to play with it a bit. And then this is actually the confidence threshold for your predictions. And so you can modify this. If you don't like the predictions that your model is putting out, you can modify the confidence interval for which it's making predictions on. So you can make it give positive predictions on data that it's less sure about or more sure about. And so the closer you get to 1, the stricter the model will be in interpreting whether a tissue is there or not. And the closer to 0 you get, the less strict you'll be. So we'll just change this all to 0.5. It's sigmoidal, so it's all from 0 to 1. So if you put in 0, it will predict every pixel is that tissue. And if you put in 1, it will say that none of the tissues are that pixel or are that tissue, just because it will be so strict. So that's what those just different numbers are. So really, you know, in terms of the outputs, when you make outputs and you want to see different colors, that's when you play with these. I don't change them that much just because I just use this like stacked output to just make sure that it looks okay. But I do change the confidence threshold to try to maximize both my precision and recall, which we can evaluate in the code. But we'll just leave it like this for now. So we'll just change it all to 0.5. And so now we're going to change the folder that we're calling from. I have caps lock on. Okay. So we're just going to say we're going to go from the FCN workflow for Craig. And we're going to do, you can just copy and paste that here. So now it's gonna read these images and train off of these images right here. Of all the images that are in the image and mask folder, it's going to use 20% for validation. This is just, this is automatically done. You can change this value. If you don't have a lot of images, you may want to increase the validation fraction from 0.2, but I'm going to train on like 20 images right now. So 0.2 is fine. This is where it gets a little bit trickier. So I often like to train like 10 models because there's some variability in how the models perform. And right now I'm training generalized models. So the idea here is Mina has annotated many leaves. I can train, she's annotated 6 slices from many leaves, and I can train on all those slices and generate a generalized model, say by training for 24 hours, that will then allow me to identify features in an image and segment them out and extract data from them at around 10 minutes per stack of images. So it really speeds things up when you use a generalized model. Instead of, I can't remember how long it takes Mason and Guillaume's code to run necessarily with a random forest. But if you have a general model, you know, in an afternoon, you can segment 30 stacks, which I think is a big speed up.
It was much longer. It was much longer when we were using the random forest previously.
Okay.
Depending on the size of the stack, it would have taken 2 hours. I mean, I'm not sure what was the experience for others. Aleka is familiar as well.
Same, yeah, same.
Yeah.
Okay. So yeah. So once you have a generalized model, this thing will fly through like 500 image stack. If the images get really big, it slows down. So when I run 2560 by 2560 images, it takes longer to do them. But that's really just this, it's the reading and saving process through Google Drive. The actual inference for each image is something around 1/100th of a second or 2/100ths of a second per image. So if you do run it locally, if Craig has like a totally badass computer that you can use, and I mean totally badass, like, yeah, you need like a crazy video card, but Craig may have it. Then yeah, you should be able to do these like insanely fast. And so yeah, it should take minutes versus hours. So it's a big speed up. So I train 10 models because there is variance to how the models perform. Sometimes they do really well and sometimes they don't. And because you can just leave this running for 24 hours or as long as you want, like, why not just train 10 or more and just like figure out which one's the best, because you can do that. And I've been training on 100 epochs. So epochs are like how many iterations that the model trains for. The more iterations, often the better. It can overtrain a bit, but basically at some point you run into like diminishing returns where if you train for say 1,000 epochs, it might not be better than 500 epochs. It just takes longer. So I've been using 100 epochs. You could train for longer than that. I think that, you know, there are diminishing returns beyond this, but it depends on the image set. For some image sets, I've gotten really good results from 500 or 1,000 epochs. So this is something you can just play around with, but we do get pretty good results with the 100 epochs. And then this batch size, you can vary the batch size if you want. It will make training faster. But if you're training on variably sized images, then the batch size has to be 1. And if you have a video card limitation, an easy way to like not max out VRAM really quickly is to keep the batch size small. The final thing is the scale. So you can actually downscale the images that you're training on, and that will speed up training and inference, and it will take up less VRAM. The problem is if you downscale your images, you will lose like small features from them. So for the leaves, I found that keeping the scale at 1 works best. So I know this is a lot, but as we go through this, you will understand it a bit more. And I'm always happy to answer any questions. So we have it set for 10 models, 100 epochs for training with a batch size of 1 and a scale of 1. And then we're going to save our output here. So we'll just check. So we have best models. I'll change it here. So we're just going to change where this output goes. And for today, just for today, I'm gonna actually change the number of models that we run to 1 and the epochs to 10. Just because I want to show you like how the model trains and then like validate it. And then show you an output from the model that we make. So we're just going to do that now. And so now we know the models that are generated will be saved to this folder, and then the name, the model group. So all the models will be saved in a folder called Craig 10 Leaf BCE P2 100 epoch, and then inside of this folder there will be 10 models that are saved, or actually in this case 1 model because we're only doing 1. And then to test our model to make sure that it's running well, we want to test it on images it did not train on. And so that's what we're doing. We're actually going to test it on a leaf that it has never seen before. And so it not only has it never seen these annotated images, but it has never seen the leaf that these images were taken from. And so we're just going to change this as well to FCN workflow for Craig. And same here, and I'll make sure that is there. We'll change this. Okay, so this should all write to the right area. So now we're just going to go through and run it. So we can run this code here. So we'll just click run in the corner. And so that code has run. And now we need to load the parameters for this code. And so this is just kind of a background operation. There shouldn't be anything that you really have to change here. So you're just going to run this. And all it's doing is something called a batch normalization. So most deep learning code needs to be batch normalized. So it just needs to like learn what the parameters are on the images it's learning from, and then it will apply those parameters to any images that it infers on. And I know my lingo is probably just like mind-numbing. So if you have any questions, don't hesitate to ask. So this part of the code takes a little bit to run. But it's just, it's just thinking. Okay.
Yes.
Go ahead.
Yeah, so I had a question about like how generalizable the models are. Are we working with the same species or all leaves, or yeah.
So
How frequently would you be like doing this model selection process?
That's a great question. So it's only trained, like this is only trained on juglans. It can do different species of juglans, but only juglans in this case. But that's because it only learned on like different juglin species. We've like applied this model from juglans to Vitis vinifera. It's done okay. Not great, but okay. But it's it's never seen a Vitis vinifera leaf. And so, if you were to feed it, if you were to add to the training data set like Vitis vinifera leaves, I'm sure it would do fine. So it just depends on how big your training set is and how diverse your training set is. You really want to capture like the diversity of whatever you're analyzing. And so, if you're only working with like Vitis or juglans or whatever it is that you're working with, maybe train on those leaves. It would be really interesting to try to make like the grandmother or granddaddy of all models, right? And like feed in all the annotated images that Andrew and Craig and Mason and and everyone else has. Mina, I know Mina's annotated a ton. I'm sure you all have too. So yeah, that could be something. And then we have like a model that just segments everything. But we haven't done that yet.
Okay, good. Thank you.
Yeah. Okay, so now we're just going to run the model training. So we'll just see how this goes. Okay, it's running. Yeah, so there it's training right now. It's just learning from the images that it's looking at. And if you get, so there's like some warnings that you could get. You could get a warning that says you ran out of VRAM. So if that's the case, like you need to downscale your images or try to get on a video card that is has more VRAM. And so that's a warning that you can get if your images are too big. Another warning that you might get is that a folder already exists. So we set this up so that it won't overwrite folders. Because you don't want to like spend a whole bunch of time training a bunch of models and then like accidentally hit like Shift Enter or something and then like overwrite them. So it just won't do that. So if you get that warning, then you have to enter in you'd have to go up to materials and put in like a new model group folder here. And that's just so that you don't overwrite things on accident. So yeah, so this model is training and you can see it does take some time to train. So we're doing 10 epochs of training. It's going to take a few minutes to do that. We're looking at this like this tensor loss here. And so we want to see this, get as close to 0 as possible. It will start to asymptote at some point. So it's kind of already asymptoting. So when it's at 1.8, still 1.8 is the best. It might get a little, it should get a little bit better, but we'll see. And so a lot of times, if I'm doing 100 epochs, 10 models, 100 epochs, I just get this running in the background and just walk away. You can open other like Colab notebooks in Google Drive and work on them like simultaneously. So, you can just kind of get this running and then walk away. And then, come back the next day. So we just have a couple more epochs to get through. And then we'll validate it. I just want you to see the validation process. And kind of how you can play with the validation. Like that's one of the key parts. You can like optimize your model. Okay, so it's done. Code's done running. Yeah. So now we can validate it. So this is just going to read this code right here. Will just read from whatever folder is. It will read from these two, the model group and the current model name folders. So if you change these, it will read from whatever you change them to. So just so you know that this section controls the validation. So now we're going to run this code. Yeah, let me just, might as well hide it. No, maybe want to see it. Okay, so here's the output. So what did we get? Well, it didn't see the veins, but it found other stuff. So these are like the accuracy. So these are a bunch of different metrics for evaluating model performance. So we have pixel-wise accuracy. So accuracy is for all the pixels in the image, how well did it predict them? So this is like true positives, false negatives, false positives. It's basically, so the accuracy is quite high in general, but you can see that there's some funny things with that. So like veins occupy very little of any given image, right? So if it says there are no veins, the accuracy will be 98%. Right? Because they're just like, there's no veins. So it can just be like, oh, there's no veins. Or there, the veins that occupy very little of the image, you can say there's no veins, high accuracy. So that's where recall and precision come in. So precision is of all the predictions that were made, how many are correct? And then recall is of all the possible correct predictions, how often did it correctly predict? And so the way to think about precision is like, if it makes a bunch of predictions, what percent are right? And then recall is of all the, like, say, veins that are in a particular image, how often did it mark a vein correctly? So that's just kind of how to define those. And then F1 score is the harmonic mean of those. So what we can see from this is that it made no predictions. That's why there's the nan. And that's also why of all the veins that are in the image, because it made no predictions, it had 0%. And then the F1 score is the harmonic mean of that. Now, here's the same. So I did 100 epochs in the past rather than 10 epochs, and I trained 10 models. And so these are the results on that same training set for that. And so what we see is that there is variation. So sometimes it will get an F1 score for the vein of like 58.58. So that's 58% of the vein. And sometimes it's higher than that. So let's try to find the best one. Okay, so in this case, it's predicting, it's the F1 score is 70%, 71% for veins. This is pretty high. I think that Mason and Guillaume's code can't predict veins quite this well. I think they're typically in the, they're getting precision and recall around 40% for veins. So we're in the 70s, which is pretty good. They tend to get the mesophyll and epidermis a bit better than this code does, but we're able to get, say, 87% of the mesophyll correctly identified, and about 90% of the epidermis correctly identified. And then the airspace is 77%, and the bundle sheath extensions are 85%. So we do okay. And so we can load that model that we just made. And it's not going to correctly predict the veins because we saw that it didn't do that. And so now we just load up the model And now we're gonna like do the image segmentation and data extraction. So we have selected a directory for it to look at, and it's going to evaluate the images in this directory, and then it's going to put an output. It's going to put the outputs into this directory right here. And so the outputs are binary images of each tissue, a CSV file with the area and perimeter of each tissue, and then a set of the tissues stacked on top of each other. And so we can take a look at that. So let's just run it. We can see how fast it goes. So it's running right now. So that's it. It's like evaluating each of those images right now. So you can see it takes about, well, it's done. So it's okay. So 3/100ths of a second to evaluate the images. And then, so we can go here and we'll just update this. Okay. So here's where the results are. There's a new folder. And we can see, so these are the predictions that got made. They're not great, but they're, you know, it is what it is. We didn't train for very long. And so you can see that it's missing the veins. It didn't make any vein predictions. And so what we also get are these, oh, of course, sorry. Clicked on vein, there's no predictions. Let's go to mesophyll. So these are the binary stacks of mesophyll tissue right here. And so you can stack these up and operate them if you want to look at like the tortuosity in the mesophyll tissue, anything like that. And this is the CSV file of the background. Say that it's the area of each prediction in pixels, and then the perimeter in pixels as well. So it has like the bundle sheath extensions and the veins, airspace, things like that. And so, yeah, so, you know, in this case, it didn't do that great. If we had trained longer, it would do well. If we go, so like we can go here, let me go look at something that I made for doula. So here's the ALS workflow. Yeah, so here's kind of what we might get. This is actually still pretty rough. I just made that one as well. Let me see if I can find a better one. Okay, yeah, so this is with like 100 epochs of training. This is like the output that you might get. And we can look at the original images here. Kind of some of the original masks. So we might have something like this. And let's see, let me pull up. So this is actually just a better way to show it. Are you still seeing my screen okay? Okay, so here's after 100, well, so here's the real original image right here. This is the hand annotated image that Mina did. And then we tested like 10, 100, and 200 epochs. And so what we see is that 10 epochs is certainly not enough to do a good job. But after 100 epochs, we start getting a pretty good result. This looks very similar to this. You can see that it struggles predicting the vein a little bit in here, right? It like kind of put this blob. But again, like, you know, if we zoom in here, you know, where's the vein? I think that if any of us were, oh Lord, sorry. If any of us were to just look at this image right here, it would probably be hard to identify exactly where the vein is. You know, we know that because we can kind of scan through the images and mark them pretty well. But if you just looked at one image, it would be hard to identify. The other thing that we can see is that there may be a vein right here. It's hard to say, but it does look like there could be a vein right here. It wasn't annotated by the human. You can see that right here, but the computer starts picking it up. After 100 epochs, it says, oh, I think there might be a vein right there. And so, you know, the computer can only do as well as it's trained. So if this was marked as a vein, you know, it might be good for the model, but you can see that at some point the computer does a very good job of finding things that even the humans are missing, and quite quickly. And you can adapt this code to any leaf, to stems, xylem. So I'm a soil scientist. I've adapted it to soils. So we want to look at organic matter, particulate organic matter in soil aggregates, and we can do that just fine. Here's the training mask, and here's the predictions that got made. They look very similar. We've done it with almond buds. So these are from Ken Shackle, right? We have an almond bud scan right here. It's the same code. We don't really have to change anything. And, you know, we can then stack things up and get these nice three-dimensional outputs, right? So here's some Amina's leaves. This is the generalized prediction. It does a pretty good job of finding the veins and bundle sheath extensions. It works for our flower tissues and it works for our soil aggregates. I've also tried it on, let's see if I can find. I've tried it on other like problems. So like, actually that's not a great example. Yeah, you know, grape leaves. How do you like segment grape leaves that you've taken pictures of on a board? We apply this to it and run a for loop, and we can extract all the data from these as well. So anyway, so it's generally pretty robust. The results are in line with what Mason and Guillaume get. Honestly, for leaves, I think that their code is a little bit more accurate, but it's a lot slower. And so like you always have to run it, you know, you have to decide for yourself, do you want to get 5% more accuracy, or would you rather be able to run like 10 times the amount of analysis? So that's kind of what it comes down to. Do you have any questions? I know I flew through that.
I think it's really great. So Devin, I was wondering, and maybe Mina, you can speak to this since you've been working with this process. So then are you to measure traits? Are you using Guillaume's code? Are you going to Fiji, just kind of and doing things manually, or how do you, what traits and what does that look like after this?
Yeah, after let's say using Devin's code, we can definitely get any volumetric values we're interested in, because we can get area, perimeter for every different tissue, and everything is calculated per slice, which is super helpful here. We can have an average, we can look at each slice individually, and then based on the resolution, you can calculate the volume. So basically you can have porosity and also mesophyll volume and mesophyll tissue. And with the perimeter, you should be able to actually calculate the surface area as well. About tortuosity, we still haven't, let's say with Devin, I know you started looking at that. So we're still not at this stage to say that we can get tortuosity from this method yet, but it should be possible. I would say why not? But one option is, if you're interested in that specific parameter, is to use the segmented stack, which is generated by Colab. and it's super fast. And then do the manual steps for locating the stomata and then run it through random forest, because the most time consuming part for the random forest code is the auto segmentation part, which takes hours.
Right.
That's one option. The other option is to keep working on this method to make it happen through this method. Is there any other? I think these are the general ones we were getting from random forest.
Yeah.
Volumetric related and tortuosity.
Yeah, that's great.
Yeah.
Thanks.
Yeah, sure.
Yeah, I think so. I haven't showed it here, but I mean, there's ways to identify the stomata specifically. It will just take some work. So like if you were to annotate stomata in the stack, say from the other, like if you were to reslice the stack so that you were looking at it like going down through the epidermis from the top to the bottom, you probably could use this code to identify the stomata. But that's something that I haven't done. I have we have the code to reslice things, to like stack them and reslice them in other directions automatically. And, for some things like veins, I mean, we might be able to get awesome results going in that other direction. I just haven't like really put the time into it. Because, let me see if I can find like, yeah. So here's like a resliced stack. See what we can see. Sorry, my computer's like not all that happy with me right now. But yeah, like you really get a good visual, right, of the bundle sheath extensions and veins from this perspective. And so that might tighten it up a bit. But it's just something that we haven't tried. It's certainly, it's not an impossible feat to do. And so, if you wanted to try it, like here, right here, you can actually see veins. They are right there. And so, it would be entirely possible to do it from this direction and put the mark the stomata. Stomata are hard to see from the other direction. The computer just doesn't see them very well, just because they're so small. So anyway, but yeah, I mean, let's see if I can find any other. Reslice things. Anyway, it's possible to run this model from like multiple directions, and then you could like stack the stacks onto restack things. It's all possible with code, right? Like it's just like additive or subtractive things. But we really haven't done that. So there's still the annotation of the hand annotation of the stomata, which is a pain in the ass, but I guess it is what it is. If you want to work on that, like I'm happy to try to get that feature running. It's just a little bit of a challenge with the deep learning code.
Yeah, I mean, I wouldn't say that to make you work on it right away. That's definitely something that I think would be valuable. But yeah, whenever whenever it makes sense for you, or maybe Mina, maybe you could weigh in on that too. But yeah, so I had another question, which was how many slices do you test and train on? What's kind of the minimum viable amount? Yeah,
I would say like if for one leaf, it's similar to what Guillaume's code is, like 6.6
Mhm.
annotated images. But here's the thing, you can make, so like, you can make a generalized model. And so after you've annotated like between 3 and 5 leaves, 6 images from 3 to 5 leaves of like a particular, I don't, sorry, my biology is terrible. Not species, but whatever level is above species. Genus?
Genus, yeah, genera.
Okay. So of a particular genus, it should be able to like segment species from that genus pretty well, especially if the images are the same size. Now, you can train models on like variably sized images as well. So some of Mina's images are like 500 by 1,000 pixels, and some are 500 by 2,000 pixels. And if you need more images to kind of mix and match sizes like that, but you can also make a generalized model that will segment like any of those sizes. Let me see if I can find an example of that. I have it here.
Yeah, Devin, if I'm right, was it from another facility we had images from, like from Swiss, that the resolution was really high and the sizes were different for widest? We have
Yeah. Yeah. Okay. So here's an example. So Mina had annotated 11 leaves. We used 5 annotated images from each. So it's 55 total annotated images to train this model. The model had never seen either of these 2 leaf stacks. You can see that they're different sizes, right? And so this is the output from those. So if you have an annotation library already, like there's a lot you can do with an annotation library. You know, because you can just feed those images in. Like you don't have to keep. That's one challenge I would say with Guillaume and Mason's code is like for every leaf you have to annotate 6 images.
That's right. Yeah, this could be really useful, Lila, for your work with Arabidopsis and the brassica, because those will all be pretty similar.
Yeah, for sure. That would definitely be better than doing each leaf.
And depending on the condition, if it's let's say, if you're looking at structural changes, if the model, let's say, recognizes everything, which does, and annotate species well, so you can actually trust the model for structural changes within the species or within the genotype group. If you're interested in dehydration, I don't know, any type of stress or kind of changes, physical changes, so you can trust the model. It can pick the volumetric changes well.
Okay. Really nice. Yeah, it's definitely getting veins a lot better than I've had success with the random forest. And yeah, it looks really good. So how do we access the folder, and how would we go about starting a project?
Sure, I will share that folder with you. Yeah, I'll just share it. I'll just make you the owner of it. And then it should work fine. We're in the process of publishing this right now. And so in the future, you'll just be able to like go to my GitHub and, do it from there.
Okay.
But yeah, anyway, I'm certainly excited for any feedback that you have, and like, happy to work with you on it. It's being used at the Pacific Northwest National Lab, and they're starting to use it at the Advanced Light Source. So anyway, that's
really awesome. Yeah.
Thanks. It's it was a lot of work.
Yeah, they look really good. Yeah.
Cool. Yeah. Anyway, cool. So I'll just share the code with you, and yeah, I mean, I can make multiple folders. I mean, so once I share the code, like you guys can just like make your folders and everything. It's pretty straightforward. How comfortable are you all with Python? Okay. How about coding in general? You all use R, right? Okay, that's good. I barely use R. I should use it more. But yeah, I mean, so if you're just comfortable connecting folders, then it's easy. If you need anything, just reach out. I'm happy to help out. So yeah, just email me.
And the same, if there was any question, I'll be also happy to chat and discuss. Yeah, we can always meet again through Zoom.
Yep.
Thank you. This has been really great.
Awesome. Yeah. Well,
Yeah,
thank you.
forward to trying it out.
Yeah. Thank you all so much. And I'll post this video into the folder as well.
Great. Yeah, thank you for making time.
Yeah, no worries. And okay, would you mind if I included this video in the publication? Okay.
Go for it.
Awesome.
Yeah.
I just wanted to make sure. Because like I need to make a training video for it. And I was like, no, this will do. Awesome. Thank you all.
Thank you,
Thank
Devin.
you.
Yep.
Thank you.
Bye.
Thanks a lot. Bye.
Yeah, of course. See if I can.
Oh, Devin, can I quickly say something if you don't mind?
Yeah, hang on. Let me turn off the recording. Is that cool? I'm just trying to figure out how to do that. I'm a Luddite.
Okay. Is it stuck?